Good afternoon. On behalf of Engineers Australia, I'm delighted to welcome you all to Designing Switchboards for a High Demand Future. My name is Amanda and I'll be your host for today. In keeping with our custom, Engineers Australia acknowledges the traditional custodians of the countries throughout Australia and recognises their continuing connection to land, waters, skies and community. We recognise Aboriginal and Torres Strait Islander peoples as the oldest continuous cultures on Earth and our first engineers. We pay our respects to them, their cultures, and to elders past and present. Before we get started, I'd like to acknowledge that today's event is being hosted with Engineers Australia's industry partner, IPD. IPD specialise in energy management and automation products and solutions, focusing on improving energy efficiency, automation, and secure connectivity. Committed to the safety of people innovation, IPD helps build a future where sustainable electrical infrastructure creates a better life for all. We thank IPD for their continued support. And today we will hear from 3 speakers, followed by a live audience Q&A. And as always, I encourage you to send questions through to our speakers via the YouTube chat box. I'd now like to take this opportunity to introduce our first speaker, Rajiv Narayan. Rajiv is a business manager for smart buildings with over 20 years' experience in electrical engineering, switchgear and power monitoring. Based in Australia, he has built his career at IPD, where he leads national sales development and supports customers across a wide range of industries. Rajiv combines strong technical expertise with commercial insights, helping organisations optimise electrical systems for performance, safety and efficiency. His experience spans product development, engineering and customer engagement, making him a trusted advisor in delivering reliable and compliant power distribution solutions. Please welcome Rajiv Narayan.
Thanks, Amanda. Hello, everyone, and thanks for joining us today. I want to set the scope first. Everything my colleagues and I talk about today is related to the main switchboard and set for an Australian low voltage distribution system. Just in case there are any international engineers watching. My role today is to set the scene and my colleagues will follow with the details. I'll cover what a switchboard system actually is, what's changed in the market and why that matters for safety, what it costs when one fails, and finish on 2 things worth specifying from day one. Let's get into it. What is a switchboard system? The main switchboard is the assembly at the start of the installation. It carries the highest fault levels, it sees the most energized access, and when it fails, the failure doesn't stay local. It reaches every corner of the facility. Distribution boards matter too, but the stakes concentrate at the main switchboard. We all know what a main switchboard does, but I want you to think about its job description. Power arrives from the grid, from a generator, and increasingly from solar and batteries. The main board takes all of that and moves it safely to every circuit and load in the building. Along the way, it stands guard and protects against overcurrent, earth faults, arc events, transients, etc. Ideally, in an installation, it's also watching load, power quality, energy, the health of its own connections, and breakers. Obviously, providing safe isolation when somebody or someone needs to work on the system without impacting the entire site. Now, what makes up a switchboard system? The enclosure and the bus bar system, the protective devices, surge protection, arc fault protection, and increasingly intelligence built into the breaker platform itself. Due to time constraints today, we will be focusing on the switchboard enclosure system requirements and cover the intelligence, the part that detects and controls things separately. As far as compliance is concerned, for a complete switchboard, you verify the complete assembly, not individual components like the enclosure system or the protection system. And that includes ACBs, MCCBs, surge, etc. Product standards are available separately for the individual components, which is not part of this presentation. The main concept here is that the main switchboard is protecting people, assets, and really the continuity of power itself. Here is the whole presentation on one slide. In the middle is the main switchboard, responsible for providing reliable, safe power. Two things are dependent on it: people, anyone who works on or near it, which brings arc flash, energized work, and a duty of care that attaches to individuals' safety. And operations, with fire risk, downtime, and continuity of supply for the entire facility. On either side are the only two things any of us actually control, and both are decided at specification. The enclosure system. A board is design verified to AS 61439, arc fault tested to IEC 61641, properly segregated and modular enough to expand rather than be replaced. And the intelligent devices for protection, arc detection, measurement, and safe operation. What I want you to hold for this presentation, the enclosure system and the intelligent devices are what provides the foundations of safe, reliable power. Selecting the right products, therefore, is essential in meeting this goal. Everything that I show you from here sits somewhere on this picture, and I will point back to it as we go along. Now, let's look at the market and the industry shifts that we're seeing. Essentially, the environment these boards operate in has changed, and so has the expectations. Solar, batteries, EV charging, high-density IT, automation are all driving more heat, more harmonics, and higher fault levels inside installations never designed for that complexity. Higher fault levels, by the way, sounds like a ratings problem. Yes, and also a safety one. Fault levels sets how much energy is available at the board, and arc energy rises with it. Exceed what the board was verified for, and you have more energy available than the assembly was ever proven to contain. So what does the market now expect of a main switchboard? Four things that we are seeing. First, from a basic distribution to safety by design. It used to be for distributing power, now also for protecting people who work on it and assets. A large portion of existing switchboards, and that installed base stretches back 40 odd years, have no arc fault protection or have never been assessed for it. Second, from a compliance only to build to last. It passed inspection, therefore it's safe. And these are not the same statements. Compliance is a point in time. Resilience is 20 to 30 years of load growth and modifications. The focus here is a life cycle and upgradability mindset while still meeting stringent compliant requirements. Third, from manual inspection to continuous monitoring. You used to find out how a board was doing by opening it or through an annual thermal inspection. Again, only a snapshot in time. The expectations now is continuous monitoring. So you are seeing a trend and can intervene rather than discovering a failure. The last one, from capacity today to capacity for growth. Board size for commissioning day, then solar and EV charging added without anyone reviewing the switchboard. And this is not a problem waiting for a solution. The platform already exists. The ABB Emax3 ACB on screen has arc fault protection with optical detection built into the breaker, continuous monitoring of load, power quality, and thermal health all integrated in one device. This, and for existing sites, the footprint is the same as previous generations. So an upgrade does not mean rebuilding the board around it. The gap between what's installed and what's needed is widening. For new builds, the path is easy, just specify correctly from the start. For existing sites, emerging technologies like the ABB Emax3 ACB is helping to solve some of the widening gaps. Early design decisions are critical. I feel this one goes without saying, but it is an important part of the presentation. The earlier a correct design is implemented, the cheaper, the faster it is, and nobody's at risk. Once the facility is operating, then that's a different animal. Now it's a shutdown or a temporary supply problem. It puts someone in front of live gear and introduces risk. Under AS 61439, major modifications will require complete switchboard re-verification. That's for the entire assembly, not just the parts that you modified. After a failure, that's happening under a work health and safety regulation. Same decision, but very different price tags. Depending on the part of the curve you're on, the curve also isn't a straight line. Cost, disruption, and legal exposure all climb together. Design stage is the only point on that curve where change is genuinely cheap. Which applications are the most impacted? Hospitals, where operating theatres, life support, and imaging all sit downstream of a main switchboard. Data centres, growing very fast with increasing uptime obligations. Mining, with very high production cost per hour, and underground, the consequences can be far worse. Utilities, where a board failure reaches the grid, and infrastructure, think train stations and the impact on daily lives. It's a huge impact. In these environments, getting the design right is absolutely critical. So what does it cost when things go wrong? Rather than tell you, I'll let Mark tell you. Mark is a Queensland electrician, 18 years on the tools, and this is a WorkSafe Queensland video of his story.
I've been an electrician for about 18 years now, and I'm very confident in what I do, and I still ended up in hospital. I've got up that day, the standard day, no thinking anything of it. I says, like, I'll bounce in and do that power quality assessment we had to do. I'd assessed the work to be done live, and I was very confident of what had to get done. It was possible to do it live. All I need to do is clip on these 4 crocodile clips, which isn't a hard task, you know what I mean? I can see the buzz bar. I've clipped on the first one, and then I've went to clip on the second one. And as soon as I've touched it, it's just went, just white, yellow flashed, you know what I mean, in my face, and just a really disgusting noise. I wasn't unconscious, but I sort of realised what had happened, and I could just smell it. All my hair burnt, my skin was all burning, and I could see all my clothes were burnt and things, my skin was hanging off and that. And I was just all black.
So when I first found out that he'd had the accident, I was at work, but when I answered the phone, I couldn't actually understand what he was saying. He was all gibberish, but all I got was, I'm in a bad way, I'm being taken to hospital. I just like panicked. Yeah.
In Mark's case, while he was working in the switchboard, as a result of attempting to pull off 2 pieces of insulation, he exposed the risk of 2 separate electrical phases. In bridging that out with his screwdriver, he's created a large arc flash with high fault current available inside the switchboard, which resulted in a large fireball which burnt Mark considerably.
When I first walked in to see him, he was in a hospital bed and he was just black, and his hair was singed. And
the injuries that I actually sustained would have been, it was actually 12% body burns, so that involved skin grafts. For that to heal, they cut all your, they grind your skin off and then lay that on top of the burn.
Further to my point, Mark is only one dimension. Other things to be aware of: fire. Electrical faults are among the leading causes of commercial fires in Australia, and switchboard faults are a well-documented contributor. A board failing thermally does not always trip. Sometimes it simply burns. Arc flash. WorkSafe Queensland has recorded 32 incidences in that state alone since 2013. 20 of them ending in hospital. And note what that number is: one state and only the incidences that were reported. Downtime. ABB's Value of Reliability survey puts unplanned downtime at close to $349,000 per hour for the typical Australian industrial business. That's the median. And that's before reputational damage and before contractual penalties kick in. Liability. Workplace health and safety prosecutions, insurance denials, inquiries. The duty of care is personal. It attaches to individuals, designers, specifiers, managers, not only to companies. If a board you specified injures someone, the questions asked will be what you knew and what you did about it. Every one of these failure costs is reduced by decisions taken before the board is ever built. What does compliance actually look like? It comes down to 2 things from the start of the presentation: the assembly and the intelligence. Before I go through, a quick orientation on the 2 standards that I have mentioned, because they do different jobs. AS 61439 governs how the assembly is designed and verified. It is the standard that says this board has been proven to do what the drawing claims. IEC 61641 is specifically on arc fault containment, whether the energy is contained and where it is directed. Really, one is about whether it was built right, and the other is about what happens on the worst day. You need both, and they're not interchangeable. The assembly has to be provable, not assumed. Design verified to AS 61439 asks for the completed Table D1. That table is the evidence. Arc fault tested to IEC 61641, which means tested containment rather than a line in a brochure. My colleagues say it goes deep on this in the second part of this presentation. Form segregation matched to how the board actually will be maintained. If someone has to work on one circuit while the rest stays alive, the separation has to allow it. Modular, so it expands rather than gets replaced. Commercially, this is essential, providing you more capability in the same footprint. The intelligence has to be integral. This is important. Protection, arc detection, and measurement in one device means no external relays, fewer wires, fewer connections, basically fewer complications. Safe operation, remote racking and maintenance mode to lower risk, health data. So maintenance is driven by actual evidence rather than a set schedule. And obviously cyber secure, like any other operational technology. The recommendation of taking both from one supply chain, one system, one verification chain, one point of accountability. When something needs to be proven to a client, to an auditor, or a regulator, you want one place to go. My last slide to bring everything together. Everything I've pointed out, the aging install base, the evolution of loads, when failure happens, is the downstream consequences of specifying decisions, most of them made decades ago. A new build hands you what a retrofit never can, a clean sheet. The decisions that you make on that sheet lock in safety, compliance, and performance for the next 20 to 30 years. All of this just boils down to two things. Specify modular, IEC 61641, arc fault tested enclosures. Genuine arc containment, expandable without full replacement, more capability in the same footprint. And demand intelligence from the breaker itself. Metering, power quality, arc fault protection, predictive maintenance. It has to be integral to the device, not separate instruments. The enclosure system and the intelligent devices. That's the whole point. Neither one is enough on its own, and both are decided before anything is built. That's it for me. Thank you for your time. Syed will now take you inside compliance and arc fault containment for the enclosure system. Milad will follow with more details on the intelligent devices part. Thanks again.
Thank you, Rajiv, for a great presentation. And now I'd like to welcome our second speaker, Syed Zaidi. Syed is the Business Manager, Switchboards and Enclosures at IPD, with more than 14 years of experience in electrical engineering, project management, estimation and technical sales. Based in Australia, he leads the strategic growth of IPD's switchboards and enclosures portfolio, working with customers across a diverse range of industries. Syed specialises in delivering compliant, reliable and efficient power distribution solutions, combining technical expertise with a strong commercial focus. His experience enables him to support the successful delivery of complex electrical infrastructure projects while helping organisations improve safety, performance and long-term value. Please welcome Syed Zaidi.
Thank you, Amanda, for the introduction. Good afternoon, everyone. I'm Syed Zaidi, and today I'll be discussing how modern switchboard system plays a critical role in maintaining electrical safety, protecting people and assets, and ensuring reliable power distribution. The electrical systems we are designing today are very different from those that existed earlier. Over the last decade, we have seen rapid growth in renewable energy, battery energy storage systems, EV charging, industrial automation, and high-density data centers. Each of these technologies places additional load on the switchboard system. If we look at the four examples on this slide, solar and battery storage introduces bidirectional power flow and it can increase the fault current. EV charging creates long periods of continuous high current, and we are installing more chargers than ever before, which means more outgoing circuits. Drives and automation generate additional heat and harmonics, placing greater stress on insulation and electrical connections. And in data centers and modern commercial buildings, we are packing more equipment into the same footprint, which means more devices, more cables, and greater number of terminations. Now, none of these technologies are the problem. They're all essential parts of the modern electrical network. The issue is that as we increase the complexity of our electrical system, we also increase the conditions that can lead to an internal arc. Most internal arc faults don't start because of a disastrous equipment failure. They usually start from much simpler causes: a loose termination, insulation breakdown over time, moisture or dust contamination, vermin, or even an error during maintenance. As engineers, we have seen the importance of good workmanship and proper maintenance. But despite our best efforts, these faults can still occur. So, in today's day and age, the probability of an internal arc is increasing. At this point, you might be thinking, internal arc faults are quite rare. Why should I spend time specifying for something that may never happen? That's a fair question. The answer is that while the chances are low, the consequences can be extremely high. As engineers, our job is to design for low probability, high consequence events. Let's discuss the impact of arc fault on various aspects. First, people. An internal arc releases massive amount of energy in milliseconds. Temperatures can reach several thousand degrees Celsius, creating intense heat, a pressure wave, and ejecting parts out. The person most exposed is the operator standing directly in front of the switchboard, perhaps carrying out routine testing or maintenance. Even if the fault lasts only for a fraction of a second, the energy released can cause serious injury if the enclosure isn't designed to contain it. Second, assets. An arc fault often starts in one location, but without the effective containment, it doesn't stay there. The pressure wave and the hot gases can spread through different compartments, damaging bus bars, circuit breakers, cabling, and other equipment. What might have begun as a fault in a single section can quickly become damage to an entire switchboard. Finally, business continuity. For many facilities, the biggest cost isn't replacing the switchboard, it's the downtime. Think about hospitals, data centers, mining operations, water treatment plants, or manufacturing facilities. Losing power for days or weeks can have significant operational and financial consequences. And since most switchboards are engineered to order products, replacement is not immediate. The important point is this: internal arc containment doesn't prevent an arc from occurring. It actually helps to give the best possible chance of protecting both people and the installation from the impact of one. Now that we've discussed about why internal arc faults matter, let's look at what internal arc containment actually means. During an internal arc test, the switchboard is assembled exactly as it would be installed on site, with the doors closed, covers fitted, and internal barriers in place. An arc fault is then created inside the switchboard. Let's look at the conditions which need to be met for a switchboard to be deemed as arc fault contained. Doors and covers should be correctly secured and not open up during the test. Deformation, however, is accepted. No flowing parts. Harmful parts, large or heavy pieces, should not be ejected out. No perforation on the enclosure on sites normally accessible to people. Indicators don't ignite. The vertical and horizontal indicators placed at defined distances must not ignite from the ejected gas or particles. The earthing circuit must remain effective, therefore, no loss of continuity. The assembly confines the arc to the compartment where it was initiated, without spreading it to other areas. And finally, limited operation capability. After the fault is cleared, specified parts of the assembly must remain capable of continued operation. Arc containment is a property of the whole assembly working together, not a rating one component carries into a board.
65 kA supply side on 1000 amp ABB MCCB.
What you're looking at here is a real arc fault test. This is a practical proof of everything we just covered on the previous slide. You can see the enclosure doors and covers are still fully attached and closed. No broken components were on the ground around the unit. Everything that was inside stayed inside. The external panels an operator would be standing next to are undamaged. Because the arc energy was directed towards the chimney and contained, anyone standing in the normal operating position in front of the switchboard would have been protected. Post-test, the earth path was verified intact, critical for downstream protection devices to still function correctly. Arc confinement. The fault was contained within the compartment it originated in. It didn't spread to the other sections. And lastly, limited operation capability. After the event, the board could safely be isolated and used by a technician without additional risk. Many people assume That if a switchboard complies with AS NSZ 61439, then it also must be protected against an internal arc. But that's not the case. AS 61439 requires the switchboard to be verified for things like temperature rise, insulation performance, short circuit withstand, earth continuity, and IP rating. These are all essential tests, and every compliant switchboard should meet them. However, internal arc containment is different. It isn't automatically included as part of the standard verification. It only becomes a requirement if it's called up in the project specifications. For example, by referencing Appendix ZD of AS NSZ 61439 or IECTR 61641. If no one asks for internal arc testing, the manufacturer doesn't have to provide it. The switchboard can still be fully complied with, say, AS 61439. That's why it's important to understand that compliant doesn't always mean arc contained. There's another point that's often misunderstood. People sometimes confuse short circuit withstand with internal arc containment. They're not the same thing. A short circuit test proves that the switchboard can withstand the electrical and mechanical forces of a fault current. An internal arc test goes much further. It looks at what happens to the enclosure during an arc fault. Did the door stay closed, whether hot gases are safely directed away, and whether people standing nearby are protected. So the key takeaway from this slide is simple. A switchboard can be fully compliant with AS 61439 and still have no verified internal arc containment performance. There are two known ways to test an assembly under internal arcing conditions. ICTR 61641 is international guidance, and Appendix ZD is a local method inside AS and NSZ 61439. They do the same job. They define how and where the arc is initiated, what is measured, and what counts as a pass. Let's do a quick comparison between the two. AS NSZ 61439 Appendix ZD is focused on the feeder load side circuits. It verifies protection against internal arc faults only in the outgoing sections, and it does not assess incomers and the main bus bar system. On the other side, ICTR 61641, it covers both line side and the load side circuits. It includes incomers, feeders, bus bars, and the dropper bus bars. In summary, it provides a more comprehensive internal arc fault verification approach. While Appendix ZD provides a practical method for verifying arc fault performance on the feeder sections, IC 61641 provides a broader assessment of the complete low voltage assembly. It evaluates potential arc fault locations across both the supply side and the distribution side of the switchboard, making it a more comprehensive verification method. Regardless of which method you choose, it should demonstrate three things. First, protect people. The switchboard should contain the arc in a way that it reduces the risk of injury to anyone standing in front of it. Second, limit the damage. Instead of damaging the entire switchboard, the fault should be contained to the affected section wherever possible. And lastly, return to service. The assembly is suitable for limited further service after the affected part is dealt with. This is a level that protects operational continuity, and it is the one critical facilities should be asking for. So far, we focus mainly on safety, but internal arc containment also provides an important operational benefit. It helps reduce downtime and makes recovery easier after an incident. Let's follow the process shown on this slide. First, you start with a verified switchboard design. This means that a modular switchboard has been tested and its performance has been demonstrated for a known configuration. It is backed by any of the verification methods as per AS 61439 to prove that it is a verified or a tested design. Next, over the life of the switchboard, changes are often needed. You may need to add few feeders, install more equipment, or expand the system as a whole. As long as these changes are made within the manufacturer's verified design rules, the switchboard continues to maintain its test performance. This change is much easier to incorporate when using a modular switchboard system. Now, if an internal arc fault does occur, the goal is to keep the damage contained to one section instead of letting it to spread throughout the entire switchboard. This can be achieved if an arc fault contained switchboard system is used. If the damage is limited, the final step is much easier. Rather than replacing the whole switchboard, you may need to replace the affected unit or module. This can reduce the repair time and minimize disruption. A well-designed and properly verified modular switchboard doesn't just improve safety, it also makes recovery faster, easier, and more cost-effective after an internal arc event. If there's one message to take away today, it's this. Don't treat arc fault containment as an afterthought. It needs to be defined as part of the design brief, not added once the switchboard has been selected. Be clear about the performance you require. Specify the containment method or the standard the assembly must comply with, whether it's ICTR 61641 or Appendix ZD of AS and SZ 61439. And finally, ask for evidence, not just claims. Request the design verification documentation and test reports that demonstrate the complete assembly has been verified to meet the specified performance. Before we conclude, I would like to briefly mention some of the updates introduced in the latest AS NSZ 61439 standard announced in Feb 2026. While we won't go into the technical details today, it is important to be aware of these changes and their impact on the industry. Group rated current, ING. Testing is conducted with all circuit breakers in the section energized simultaneously to account for their combined heat dissipation. This verifies the current rating of each breaker under mutual heating conditions. The new standard now covers PV assemblies as well, with requirements introduced under annexure DD, EE, and FF. And lastly, solar and thermal exposure. Outdoor switchboards are exposed to significant thermal stress due to a combination of ambient temperature and direct solar radiation. Previous versions of the standard provided limited guidance on how to assess these conditions. The updated standard introduces clear requirements for the testing and verification of switchboards subjected to solar and environmental heat exposure, ensuring improved reliability and performance in demanding Australian climate. Please note that these revised requirements will come into effect from Feb 2027 onwards, following the transition period provided for industry adoption and implementation.
I'd now like to welcome our third and final speaker, Milad Mostofivala. Milad is a Senior Product Manager at ABB. He assists clients with achieving their energy efficiency targets within electrification. For 15 years, he has been consulting with clients across small, medium, and large enterprises, including commercial, industrial, and government sectors, supporting them to incorporate Industry 4.0 capabilities with data, connectivity, and analytics interface into their electrification systems. Milad is a practicing registered senior electrical engineer with expertise in power and energy distribution in electrification. He is an alumni of Royal Melbourne Institute of Technology and the University of Melbourne, Melbourne Business School. Milad shares a passion for sustainability within electrification and engineering energy efficient distribution systems. Please welcome Milad Mostofivala.
A very good afternoon to you, ladies and gentlemen. It's always a pleasure to be invited back by Engineers Australia for another round of Industry Partner Series presentation. What I have been asked to talk about today and present for you is around strategies for enhancing the electrical resilience and safety within the electrical distribution system. Technically, what I have prepared for you today was to talk about some of the latest key challenges that we are facing at the moment within our electrical distribution sector. And I'm going to talk about some of the design principles that can assist solving these challenges. I'll describe briefly in terms of why some of these methods are outdated or there is a need for change. And after that, once we talk about some of these design principles that can assist you as a cohort of electrical engineering colleagues, I'll quickly talk about the latest technological advancements that is available for those design principle implementation. And I'm going to talk about a few real case studies that I have been lucky enough to be part of with my friends and team within ABB and IPD. And I wish that you will enjoy these few chapters, and in the end I will wrap up with a demonstration video that I think can benefit you as the audience to understand some of these technologies. So let's start. The key challenges that are faced in our industry at the scale at which we are moving forward is around arc flash hazards. That is a never-ending problem, as my colleagues Raj and Syed described earlier, in terms of the incident energy and the risk that that possesses to the electrical system. The thermal stress is also another factor that is causing quite a huge amount of heat management need, technically. And in terms of integrity of connection as well, because of the amount of high current that's taking place within the distribution system over a period of time, this thermal losses causes a bit of a mechanical damage and issues. And fourthly, the compliance are ever stringent. They are constantly increasing, and the regulatory compliance are very sophisticated these days around the topic of safety, around the topic of adherence to the standard. And the fifth element of what we are facing in our industry right now is around the aging infrastructure, which is becoming more difficult to provide a very perfect outcome in terms of managing that maintenance risk itself. So if we think of a typical application examples, which is some of the recent projects that we are working at the moment, is around utility substations, around industrial plants, around hospitals or data centers. Within a 415 volt AC environment, the requirement for current is ever increasing, and clients constantly need to draw out additional current, and that increases the KA rating that they are required to be able to safely break in case of any tripping event or any switching event. So the high available fault current is creating potential for extreme incident energy. And with that situation, there are three hazards that is being created. First and foremost, as my other friends described earlier, are around the arc flash events itself. Secondly is around the thermal overload that the heat buildup can cause. And thirdly, the maintenance practices that are conducted within the electrical system is quite a critical item with the change that we are facing within our industry. The traditional methods are getting a bit outdated, obviously. The thermographic measurement that requires constant check by different personnels, the periodic adherence and periodic presence on site that may cause regular shutdown or plant outages is also becoming outdated. People can't afford to, shut down any ongoing, production at the same time. And that could be for, maintenance reason. That could be for even continuous operation. And on top of that, there are challenges in terms of, safely conducting all these factors and reducing the risk that's involved. And as an engineers, we are tasked to provide solutions and methods to assist the end client and personnel on site to constantly push forward with reduction of risk. So let's talk about integrated arc flash protection as the first category. The key challenges within arc flash protection is around the fault clearing and clearing that incident energy. And the overcurrent protection devices, in terms of their arcing time, there is an ever need within the end clients to reduce that clearing time. And there are always coordination complexities in projects and places that I've worked with. And because of the rise of renewable energy generation, the battery systems, the solar systems, the inverters, their integration increases the unpredictability and the fault current that happens within any given site. The infrastructures are also aging. Sometimes we are not working on a brand new greenfield application. We are looking at a very old infrastructure that we need to just maintain. And there are constantly challenges in terms of, creating a safe regulatory, up and running site in terms of creating that arc flash proof facility. So because of that, one of the design principles that can assist the industry and that can assist the projects with are having a few aspects in mind, such as trying to minimize that arcing time between our design and systems. So reducing that arcing time to 50 milliseconds or less can definitely address some of these problems. The complex arc detection system itself can be relooked at and reevaluated by utilizing high-speed current limiting systems in place. That can be through, any kind of optical fiber sensors or being able to, utilizing that tripping threshold. But what's important here is also considering the, reduction of that arcing time by creating that protection functionality within the circuit breaker itself rather than any other external devices. So that design principle can definitely assist to address some of these challenges that the industry and segments are facing right now as we travel across. Some of the innovative technological advancement that is out there and is available is obviously having a fiber optic sensing mechanism in place. Those types of detectors can quickly reduce the fault clearing time to less than up to and less than 50 milliseconds. The arc flash relay itself that is available outside the market are quite reliable in terms of I-squared light detection that they achieve, in terms of prediction as well. And there are available pattern recognition solution that can detect conditions in terms of the pattern of behavior that a load system kind of behave. But on top of all of them, I think one of the most interesting one that can be used is the integrated arc flash detection that has compliance to 60947-2 standard. And that technology reduces the necessity for any external detection, and it can improve the fault clearing and eliminating the incident energy by less than 50 milliseconds as well, which is quite interesting and important to highlight and use as a design principle. introducing you with a case study that I was privileged enough to be able to assist with was a data center customer in Sydney that had quite a number of, distribution system switchboards, and within that site and design that they had, being a data center, they had very restricted or essentially once a year maintenance requirement. And within that client requirement, I think one of the key aspects was to be able to create the current sensing and arc clearing time to less than 50 millisecond, which we were not able to achieve with any external detection devices, and we had to improve that and emphasize on the fact that we use the integrated arc flash devices within the circuit breaker itself to be able to fasten that clearing time. I think one of the key results for that client in this project was that their insurance premium was also reduced because of the compliance that they were able to pass given this new arc flash detection technique that they could utilize within the system. There was also another interesting outcome that before, because of the way the site and the facility was designed, there was a stringent requirement for the personal protection equipment of higher category, and because of this they were able to come up with additional saving in terms of what they must adhere to from a category 4 to a lower category item in terms of the PPE for the personal or subcontractor or the people who visit their sites. Next, thermal monitoring. In terms of thermal monitoring and temperature itself, obviously thermal runaway is the precursor for any electrical fire and switchgear failure. And as we all know, loose connections, overload, insulation degradation, they all cause and create that level of heat within the circuit breaker terminals or within the joints and cable connections. And the conventional practice around thermography inspection during scheduled outage is obviously being practiced quite regularly, but there is quite a number of limitations in terms of the inspection cycle, the availability of relevant personnel to be able to conduct such monitoring and detect or take out any outcome from what they are trying to achieve there. There is often problems that these kind of practices are not 24/7 as much as some sites may like to run them every quarter per year. I think there's also a missing piece in terms of that temperature performance detection to a bigger, SCADA or building management system monitoring that can create a sequential fault detection or fault clearance. And obviously, as our clients' load is increasing and their demand for higher current increases, there's an ever increase in the temperature that's going to be drawn within the distribution system, and specifically around the applications these days. I think that causes additional need for thermal monitoring that makes it outdated for the traditional method of going physically and creating that window. So as I mentioned, there are barriers in effectiveness of the traditional methods. The access constraint is always there. There is sometimes the volume of data that needs to be analyzed in terms of the infrastructure can cause some issues. Calibration is sometimes, I have seen, create some misleading outcome in terms of what needs to be done, and the having a kind of a monitoring system in place can create a bit of a confidence for people who are running the asset in terms of the performance. Unfortunately, there's also a compliance gap that within the S3000 there is no mandate around thermal monitoring for the LV asset as we speak today. Some of the key design principle that can change this or fix this and improve it is obviously moving to a continuous, sensor-based thermal monitoring, and that could be types of, monitoring that can happen at the connections, joint places within your switchboard system that has higher current activity, and creating a bit of a logic or a system in place that can alert or alarm when a section of your switchboard or distribution system is starting to become or behave in higher than expected temperature format. Obviously, if this can be sensed through sets of sensors that can communicate and talk and signal, we will be very happy and very sophisticated with that. But obviously, there's never that luxury present that can have a correlation between the way the load behaves and the temperature kind of performs. But shifting that principle in design, I think, can definitely benefit and create a positive outcome for the end client significantly, to create that level of relation between the load profile and the temperature monitoring. Some of the technological advancement that we have within this area is around being able to detect through fiber optic sensing. Obviously, that has always been there. There are a range of wireless sensor technology that's available there that could be quite interesting to utilize within the switchboard system itself. The infrared types of camera detection and utilizing them is also quite interesting. But one technological advancement that I think and I believe can really benefit is to marry the detection and the sensing with the processing power of the circuit protection to be able to create or cause alerting and signaling prior to any trip event, and that would be to set a certain temperature and being able to send a signal when certain temperature on certain feeders are achieved, and being able to co-create this level of competency within the design itself. One of the cases that I was able to kind of participate in with the team and the client brief was around the thermal monitoring of an iron ore processing plant, where in this case the client obviously has a very high cost of outage if there is the outage that occurs on production line, and the way that their load profile behaves is having a lot of machineries and high current systems in place within their facility. It has a lot of temperature increases within the given the motor loads and the conveyancer loads that they are using, has a lot of potential for over temperature within the distribution system itself. What we tried to implement for this client was to use the embedded sensor technology within the switchboard itself, and marrying that with the CPU or the brain of our circuit protection devices, and creating that level of correlation was assisting this client to reduce the number of unplanned outages that they had throughout the year, and it also helped them to shift from the time-based, scheduled, kind of maintenance service level to a condition-based service activity. And thirdly, around keeping the personal safe during switching is around remote racking. So obviously, racking is the activity of withdrawing or drawing out a circuit breaker from its cradle. There are personnel who need to be in front of the switchboard system to be able to, conduct this. They have to set a boundary. Fortunately, some facilities have the luxury to plan for a shutdown. Unfortunately, some others don't have the facility and they need to keep the switchboard alive, and they can only afford to have a tier of the board, to a lockout, tagout, system. And after creating their safety work method statements that they need to do the switching, that's the only time that they can actually conduct such rack out operational performance. The challenge there in terms of safety is obviously the unfamiliarity of the personnel is always a challenge, because sometimes people are trying to operate switchgear that it's not very known to them in terms of the steps in which they need to take, and sometimes there is openness within certain facility that they would like to adapt the remote tracking devices in place. Obviously, they do have a benefit, and they do cause or create a safe kind of procedure in terms of conducting the remote racking itself. Obviously, some of the lockout, tagout protocols need to comprehend or include the remote tracking device itself as some of the steps to be able to conduct the actual operation. But I have often been involved or seen situations that the portable kinds of remote racking devices are creating a bit of a difficulties in terms of actual operation, and they do create a level of risk. And because of that, I think one of the design principle that can improve that part of our design structure is trying to think of new methods in which remote racking can be done, and think of ways that remote tracking can then be integrated with a maintenance kind of a switch or a maintenance kind of a operation. So items such as reduced energy let through operation that can operator switch prior to acting or doing any rack out mechanism, and that can create a much safer atmosphere for people who are familiar, not familiar, and in general for the end clients in terms of their facility that they're looking at. Obviously, there are existing remote racking devices that can be used around all switchgear. But I think one of the interesting technological advancement that we have within this area is around the embedded remote racking that can definitely, dismiss the kind of external device problems that takes to install and position in front of switchgear. When you're having the embedded devices, they are obviously much more easier to operate. They are less risky for the maintenance team, and the way they connect and the way they work can be adjusted or cooperated with the maintenance switches that you use in terms of your energy led through management of the asset itself. And at the same time, it removes any barrier in terms of access or connection in front of the switchboard if they have a problem with creating lockout, tagout, or working to the statement in place. So one of the case studies that we've been able to assist a client with was around a LNG processing plant. That was a confined space kind of switch room, and they had a bit of a high incident rate. Well, when we say high, they had two incidents every 2 years. They had an incident during the rack out procedure. Obviously, because they were using different kind of subcontractors to attend to their site, and they had quite a rigorous number of racking operation as well because of the testing that they wanted to conduct in a planned manner. So what happened as an outcome was this client was open to try some new design. So within the design implementation, we proposed the embedded remote racking device to them. And when we were doing the due diligence before actually conducting or rolling out this to their facility, was very clear that the benefit is there to be able to even remotely conduct the remote racking devices through any supervision system, and simultaneously being able to marry that remote racking operation to a safety switch, which is essentially a RELT or a reduced energy led through switch that changes the whole setup to a maintenance mode. So in this project, we completed the design stage on this proposal, and I think the client is getting ready to start to roll out the systems within their facility and site. So coming towards the end of the presentation, if I'm to kind of suggest any implementation roadmap given the topics that we discussed today, I think a phased approach is always very much important. And if I am to suggest any outcome to you guys as an engineering cohort, I think phase one, always assess the arc flash that you have or the incident energy that you have for your client. Start by auditing the switchgear that you're looking at. The second phase is always to design, review the design criteria itself, and take a look at what are the options that you have in terms of improving that design. And obviously, if you are open to provide the specifications that can, include these three criteria around remote racking, around embedded remote racking, thermal monitoring, or in terms of integrated arc flash studies, I think that's a good step forward to bring that into your design principle. And third step is obviously deploying these methods or systems in place and then sustaining them and their operation for your end client, hopefully for the next 5, 10, 15, 20 years after lifetime. And I'm just going to wrap up the presentation with a graph that is providing a comparison between the incident energy reduction that we have through a conventional over current protection device that you see on the red graph. And you can see that the 28 calories of incident thermal energy per square centimeter is what's recorded there. If we are to use an external arc guard relay that we have, obviously there is a significant reduction from 28 to 8. And if you are to use the integrated arc flash detection devices, you will be able to significantly reduce that to 0.4. Obviously, there is quite a significant change and shift that can create a safer atmosphere. So with that, I would like to thank you for your attention, and I would like to complete the presentation by bringing in a demonstration video of how some of these aspects around integrated arc flash can be implemented within your switchboard system.
Thank you to our speakers today for your insightful presentations. It's now time for our audience to get involved for the Q&A. Just a reminder to please ask your questions to the speakers via the chat box, and don't forget to let me know who your question is directed to. Thank you to everyone who did submit a question while registering for the event today. I might start with some of these questions and bring back the panel as well. So Raj, I might start with you. Who pays for verified arc fault tested boards on a competitive tender?
That's a great question, Claire. Look, I find this to be a specification problem rather than anything else, than a cost problem, if you like. It's also a safety question. If you specify 61439 table D1 and 61641 in a spec, and essentially every tender then prices the same thing. So essentially you're setting the baseline. In critical buildings, that's a small difference against an outage. And you still have a duty of care either way from a work health and safety perspective. I think that answers the question.
Thanks, Raj. I've got a question here from Chris in New South Wales for yourself, Saeed. Can IPD do drawings and designs and even build the panel, or do they only assist of supply or equipment?
Yeah, sure. So basically, IPD can support customers with well beyond simply supplying components. We do have in our team the capability to assist with main switchboard design, drawings for the GA, for the configurations, providing design verification documentation, component selection, and we also have the capacity to provide a completed table D1 form of AS61439. That is a very critical document that people should be asking for. And then we also work closely with approved switchboard manufacturers who we have trained, and we can take those designs to the shop floor for manufacturing and assembly. One key point that I would like to point out is that the final responsibility of the manufacturer and the completed assembly, it sits with the switchboard manufacturer. And this is there's a clear line drawn under the 6143 line between the responsibilities of our original manufacturer and assembly manufacturer. Thank you.
Thanks, Saeed. Milad, I might jump over to you. A question that's come from Smiratha in Asia. It's a bit more of a technical piece. For data center critical boards, power boards specifically, how much do you oversize versus a standard commercial industrial board, and why?
Fantastic. That's an excellent question, Samarata. From the project example that I have worked with and I experienced, the way I would segregate or consider the entire system is around, firstly, this main switchboard itself. Second level would be the sub-distribution that is PDU or RPP. And then third level would be the rack PDU. And from what I have seen, for example, when the calculated analyzed KA rating was to be at 50 KA, I have seen that our design engineering colleagues are always doubling that to 100 KA. I have even been in projects that has pushed further to 120 KA for that main switchboard section. Following through on the next level within the PDU and RPP, for example, I've seen that when the calculated rating is around 14 to 20 KA, and typically design engineering teams are again doubling it to 40 to 65 KA in terms of eliminating it. And a similar fashion in the rack PDU format too, when the calculated fault is around 5 to 10K, I've seen that they have gone to 20 to 25 KA rating. I think there is an important factor here that when you're looking at a data center kind of application specifically, even because the nature of the IT load itself is, and obviously the harmonics that they possess. Typically, I have also seen that the neutral calculation are rated to 200% in order to avoid any kind of fire or heat rise and trying to mitigate those risk factors. So quite critical and at the same time quite sophisticating in terms of design criteria. Thanks.
Thanks, Milad. Raj, back over to yourself. There's a question that's come through the chat box here. Is an arc flash study mandatory in Australia?
Another good question, Claire. So not specifically mandated, but the obligation is to assess and control the risk, right? So under work health and safety, again, legislation, you must eliminate or minimize risk so far as reasonably practicable, right? So it is actually whoever's designing the board needs to conduct a study in order to do that. And I think with Mark's case that, the videos that we've shown, there is risk and therefore it needs to be assessed and controlled. It's not mandated, but there is, again, a duty of care. Thanks.
Thanks, Raj. And a question for yourself, Saeed, that's come through in the chat box as well. What is a major modification according to AS 61439, and how do you distinguish between minor and major modifications?
That's a good one. Actually, 61439 doesn't really define a major or versus a minor modification rule. The practical distinction could be whether the modification affects the design characteristics that has been verified. So, for example, if there's a like-to-like component replacement that may have little impact, it may be allowed. But when there's a changing of busbar system or protection rating or a current rating that can actually affect the temperature rise and the short circuit rating of the board itself, in those cases, the design verification needs to be reassessed rather than just simply assuming that the original certificate still applies. So if you're going to that zone, you have to reassess the whole design verification documentation completely. I think that answers the question there.
Thank you, Saeed. And I might just stick with you on the standards for the 61439. When does the new 61439 come into effect, and what's the cooling period? So we've just had that in the chat box as well.
Yeah. So basically, the new standard was actually published in Feb 2026, And there's a 12-month cooling period when from the published date of the standard. So from 2027, Feb 2027, that's when the new standard gets mandatory to be used.
Thank you. And a question here, Millard, for yourself. There's two questions that are quite similar, so I'll ask both. What is the maximum arc flash fault clearance time from ABB's relay and circuit breaker? And what is the difference in the arc fault clearing time? So with the EMAX2 and TVOC systems.
Fantastic. So I think one was addressed from Vaden and the other one was from Grish, if I'm not
Yeah.
mistaken. So great question from you guys. Obviously, within the older design on Emax 2, we've been able to achieve a fault clearing time of approximately 45 to 60 milliseconds. And within the Emax 3 range, we've been able to push that further down to 40 milliseconds. Obviously, there is a use of integrated arc flash protection system in place that can assist with that level of improved clearing time. Thanks.
Thanks, Millard. And Raj, I might come back to you. Can you explain compliance is a point in time?
Another good one, and probably an important one, this one. A board is verified against declared conditions, right? Fault levels, ambient temperature, load profile, diversity factors, things like that, right? Over time, the board, the load changes, but unfortunately, the board stays the same. The question here is whether it's still fit for purpose for today's or current loads, and that loads actually bring harmonics, higher temperatures, which is related to temperature rise, a different diversity assumption potentially, and in some cases changes to the fault behavior. So compliance done at initial install doesn't always reflect current conditions. Thanks, Claire.
Thanks, Raj. And I might just come back to yourself, Millard, for a question that we've had come through from Anu here in the chat box. Is arc flash boundary distance defined with door open or doors closed?
Yep. So based on my knowledge, obviously it depends on which standard you'll be looking at in doing the calculation. I've obviously worked with quite a number of US-based customers and data centers, and they refer to the NFPA 70E, and that does call out for the door open scenario. As a professional engineer, I would like all the standards to have the arc flash boundary as an assumption that the door is open, because the purpose of all of these are around making sure that the workers to live elements are not exposed. As far as the Australian standard, there are different incident energy levels that's calculated, and they also call out for both scenarios in terms of door open and door closed. So from memory, AS 0667, if I'm not mistaken. I hope that answers the question. Thank you.
Thanks, Millard. And Syed, I might jump back to you. Question here. If the board has an arc fault detection system, do we need containment?
Yeah, so basically the detection and containment, they address different types of risk. Basically, what happens in terms of detection, it basically works on to operate very quickly to detect the arc and to initiate protection. And it helps to reduce the energy and the duration of the arc fault. But even in that fraction of a second, as per the previous slide decks that we have shared, there is still significant arc pressure and hot gases and thermal energy that has been released into the switchboard system. That's where the physical construction of the switchboard becomes more important. Containment is actually designed to control the effects of the internal arc and prevent them from getting outside the board or affecting different parts of the switchboard system. A Techno module switchboard system has been tested for arc fault containment. So I would say, rather than looking at them as a replacement, detection as a replacement for containment, I would see them as a complementary layers of protection for a switchboard system as a whole. I think that answers the question there.
Thanks, Saeed. I might just stick with you as well, just talking around the containment. There's another question here. Does internal separation form 4 automatically provide arc containment?
That's a good question, actually. See, with internal separation, it can provide segregation and limit the interactions between the different functional units, but it should not be confused with the verified internal arc containment. The answer for that is no. A form 4 board can still fail an arc fault test if the door latching or the pressure relief chimneys or the barriers were not tested or not engineered for arc pressure specifically. That's why I would say that a Form 4 board automatically does not mean are contained. A Form 4 board tells you that the board is well separated. The components, the functional components, the functional units are in different sections. But in case of a fault, it doesn't tell you what happens to a person who's standing in front of an arc. That's a complete different test.
Thank you. And we are getting close to the end of our session today. Malad, I've got another question here from Waden here. So can you explain, does the relay support the IEC 61850 communication?
Fantastic. So 61850, always an excellent communication protocol standard that can be used across the low voltage and the medium voltage or the high voltage system. Within our portfolio, yes, we do accommodate for that. Both traditionally on the Emax 2 series, we always had this protocol available. On the new Emax 3 series as well, we also support the simultaneous integration of all the elements that we talked about in terms of arc flash safety and reduced let-through energy, and we can accommodate that in conjunction with the 61850 protocol as well.
Thanks, Malad. And we have got to the end of our session. Before I do close up, I'd like to throw to our speakers to share with us one or two key takeaways that you'd like our audience to take off from today's session. I might start with yourself, Raj.
All right, thanks, Claire. All right, so my key takeaway message, and I'll keep it simple. In critical buildings, failure is not an option, right? You can expand that out to commercial buildings as well. Literally, is how safe can you make the building? It comes down to protecting three things: people, asset, and continuity of power. Specify it correctly the first time with the right products. That's my entire key message there. Just be aware that you also have, work health and safety regulations to follow, which I think, and judging from the questions that we've been getting, we've been missing that point throughout the session, but it's there. That's it for me, Claire. Thank you very much.
Thanks, Raj. And Saeed, yourself?
Yep. So the key takeaway for me, I'll try to keep it brief. As we see, there's the risk of internal arc is increasing in this day and age, and detection and protection can limit the energy release, but also the construction of our assembly determines how that energy is contained in a switchboard system. You've just seen the video with Mark getting injured, and we don't want anyone else to get injured like that. So basically, we should be driving towards a specification document that should address both protection and containment. That's for me.
Thanks, Saeed. And Malad, lucky last.
I'll be very quick to wrap up. For my colleagues, I would suggest what I normally suggest during this forum. Always push forward with adapting the brand new technologies. They are tested to essentially fix and solve our problems, and don't hesitate to influence to adapt these new technologies. Thanks.
Thank you. And that is all we have time for today. Please join me once again in thanking Raj, Saeed and Malad for their time and input in today's session. I'd like to thank Engineers Australia's industry partner, IPD, for their support and partnership. If you don't mind, please completing a short feedback form, which is linked in the description box below, to help us always improve and plan for future sessions. I also encourage you to subscribe to our YouTube channel to stay across upcoming content. As always, we encourage you to get involved with Engineers Australia's events. Please scan the QR code on your screen to view and register for an event that's coming up online or near you. Thank you again for joining us, and we hope to see you at our next Industry Partners event.